Hey there guys, how's it going? Mike coming back at you here with another video on Calculus 1. In the previous video, we talked about how continuity plays a big role in some big theorems in calculus. We introduced the Extreme Value Theorem, or EVT for short. We talked about what this theorem lets us do, specifically tell us when we have a when we have a minimum and maximum value of a function on a given interval. And we also went through a 4-step process to help us figure out what those minimum and maximum values are. Just as a quick recap, you're given a function f of x, you're given some interval, and you're asked to find the minimum and maximum values of f of x on that interval. First thing you always have to do is check to make sure that both hypotheses of the theorem are satisfied. You have to have a closed and bounded interval, and by that we mean both endpoints of your interval have to be finite real numbers, and the bracket on each of those endpoints has to be a square bracket. And the function has to be continuous over that entire closed and bounded interval. So once you check that both of the hypotheses are satisfied, you're then going to find the stationary points of f of x. That is to say, you're going to find f prime, set it equal to 0, and you're going to solve for x. Then you're going to take the stationary values, those stationary points that lie within the interval that you're given in the problem, and you're going to carry those into the next step, the fourth and final step. Then lastly, step 4, you're going to take each of those stationary points that you carried over from step 3, as well as each of the endpoints of your given interval, and you're going to substitute each of those into your function f of x. You'll get some numbers out. The largest value that you get out is the maximum value of the function on the interval, and the smallest value that you get out is the minimum value of the function over the given interval. So we're going to see how this process gets used with some practice problems here. There we go. We're going to find the minimum and maximum values of 1/3 x cubed minus 5x squared minus 24x plus 3 on the interval -4, 3. So step 1, make sure that both hypotheses are satisfied. Do we have a closed and bounded interval? Yes, we do. Both endpoints, -4 and 3, are real numbers, and the bracket on each of these endpoints is a square bracket. Is our function f of x continuous on this closed and bounded interval? Well, our function f of x is a polynomial. Polynomials are continuous for all real numbers, so yes, both hypotheses are indeed met. So we can continue on with our method, and the EVT guarantees that we do have a minimum and maximum value. I need to differentiate f, set it equal to 0, and then solve for x. When you differentiate f, you get x squared minus 10x minus 24. Set this equal to 0, and we factor that quadratic there. It breaks down to x minus 12 and x plus 2, which means that the two x values which make this product equal to 0 are -2 and 12. So this is the end of step 2. We found our stationary points, those stationary values. Now, for third step, I only need to take the stationary value or values that lie within the interval that we are given. I only need the stationary points or stationary values that lie between -4 and 3. Looking at these two x values here, there's only one that lies between these two numbers, and that is -2. So I'm going to take -2, and then I'm also going to use the endpoints of this interval in step 4. So for step 4, we take these three values, -4, -2, and 3, substitute each of these guys into our function f of x. we find that f of negative 4 is negative 8/3, f of negative 2 is 85/3, and f of 3 is negative 105. Whatever is our largest value, that's our maximum value. Whatever is our smallest value is our minimum value. So the largest value we get is 85/3. Smallest value that we get is negative 105. So these are our minimum and maximum values. So this was a pretty low-key, pretty nice first practice problem here, just getting our feet wet into the use of this process. Next thing I want to show you is just one case as to why we have to check that both hypotheses work. Why we have to make sure that both of our hypotheses are satisfied before we can conclude that there is a minimum and maximum value for our function on a given interval. We're asked to find the minimum and maximum values of 2 divided by 3x minus 2 on the interval negative 1 comma 2. So, first thing we do, we check our hypotheses. Do we have a closed and bounded interval? Yes, we do. Again, both endpoints are finite real numbers, and the bracket that we have on each of these endpoints is a square bracket. But is the function f of x continuous on the entire closed and bounded interval? Is 2 divided by 3x minus 2 continuous for every x value between and equal to negative 1 and 2? Well, f of x is a rational function. F of x is not defined and thus not continuous for any x values that make the bottom equal to 0. If I take the bottom, 3x minus 2, and set it equal to 0, it is pretty straightforward to find that x is equal to 2/3. And last time I checked, just using basic knowledge of numbers, 2/3 does indeed fall between negative 1 and 2. So the function is not continuous for every x value in this closed and bounded interval. And thus, we cannot use the EVT. We cannot say that there is a minimum and maximum value by use of the EVT because the function is not continuous on the closed and bounded interval. In fact, if you take a look at the graph of f of x here, this thing has a vertical asymptote at x equals 2/3. So it's skyrocketing up one way and then skyrocketing down from the other way. So this is just one sample as to why you have to check those hypotheses to make sure that they're both satisfied before you continue on in this process. Our third and final sample here, find the minimum and maximum values of the cosine of x on the interval negative pi over 4, comma 5 pi over 4. So pause the video right here. Go through this problem on your own. Use that 4-step process. First of all, figure out whether or not we can even use our theorem to find a minimum and maximum value. If we can, then go through the rest of that process. So pause it here, take some time, try to figure out what the min and max values of f are, if there is even going to be one, and then start it back up, and we'll go through it, and we'll see what the end result is. Okay, so let's see what happens when we run through this problem. First thing we have to check, are the hypotheses satisfied? Well, our interval is indeed closed and bounded. We have 2 real numbers in there, and we have square brackets on each of those numbers. So first one is good. Second one, is the function continuous over all real numbers? Well, the cosine function, cosine of x, is continuous for all real numbers. So yes, the hypotheses are met. Therefore, the EVT guarantees that we have a minimum and maximum value for this function on this interval. Question is, what are they? Now we go into the rest of our process. So now we're going to differentiate f. We're going to set it equal to 0, and we're going to solve for x. We know that if we take the derivative of cosine x, we get minus the sine of x. So we take minus sine x, we set it equal to 0, and we solve for x. And we think of what are all the x values that make sine of x 0. Well, thinking of our lovely unit circle, the x values that make sine of x equal to 0 are all whole number multiples of pi. So 0, pi, 2 pi, 3 pi, 4 pi, so on and so forth. And then going backwards as well, minus sine of minus pi, minus 2 pi, minus 3 pi, and so on and so forth, going to the left as well. Now, we only need to carry on into step 3. We only need to take the x values that lie between negative pi over 4 and 5 pi over 4. Of this infinite list of x values, there are only 2 x values that we need. We only need 0, and we only need pi. So we're going to take those 2 x values as our stationary points, and then we're going to take the endpoints of our interval, negative pi over 4 and 5 pi over 4, and those are each of the guys that we're going to plug into our function f of x in step 4. So when we plug each of these guys into f of x, into cosine of x, we find that f of minus pi over 4 is radical 2 over 2, f of 0 is 1, f of pi is negative 1, and f of 5 pi over 4 is minus radical 2 over 2. So whatever of these is the largest value, that's our maximum value. Whatever is the smallest value that we get out here, that is our minimum value. The largest value here is 1, and the smallest value here is negative 1. So these are the maximum and minimum values of cosine x on this interval. Now, something I want to make very clear, and this is something very important to keep in mind. The maximum and minimum values of your function are all dependent on the interval over which you are looking. You could be working with the same function, but if you use 2 separate intervals, you could come up with 2 different sets of answers. As a case in point here, we saw that the maximum value on this particular interval for cosine of x was 1, and the minimum value was minus 1. If I change my interval, though, say to be from pi over 4 to pi over 2, what we would find is that there would be no stationary points between pi over 4 and pi over 2. So we'd only be plugging in the endpoints into cosine x, and those guys would be giving me the min and the max value. The cosine of pi over 4 is radical 2 over 2. The cosine of pi over 2 is 0. So in that case, our minimum value would be 0, and our maximum value would be radical 2 over 2. So, important thing to keep in mind, values depend on the interval. So, this is our wrap up for the EVT. This is our video where we saw some sample problems as to using this four-step method associated with the extreme value theorem to find minimum and maximum values of a function on a given interval. In the next video, we're going to move into the other big theorem that relies heavily on continuity, the intermediate value theorem. If you have any questions or comments, be sure to drop them in the comment section below. Otherwise, until the next video, take it easy.